Rational equations and inequalities. To solve for x algebraically in this rational equation, we need to first determine what the least common multiple or the least common denominator is of all of the fractions that we see. In order to do that, it would be easiest to factor everything first. So if I were to factor this denominator, it would factor into x minus 6 times x minus 2. So we can now see all of the pieces. And we can see that x minus 6 repeats. So we only need to write it in the least common denominator once. And the same thing goes for the x minus 2. It's repeating itself, so we only need to write it once in the LCD. Now, in order to have all of the denominators cancel out, because that's what we want to happen when we have an equation, we want the denominators to cancel out. We're going to multiply this entire thing by the LCD. Now, I'm going to write it out so that you can see what's happening. So basically, the 1 is getting multiplied by the x minus 6, x minus 2, and the denominator is still x minus 6. The x is also getting multiplied by the LCD, and the denominator stays x minus 2. And the 4 is getting multiplied by the LCD. And I'm going to write the denominator in its factored form so that we can easily cancel things out. Now, you don't need to write it out this way. If you understand that when you multiply by the LCD, these cancel, the x minus 2 cancels, and this cancels, you don't need to show that you distributed. You can just write it out as 1 times x minus 2 plus x times x minus 6 equals 4. We're going to simplify. And then we need to get it into standard form. So I'm going to combine the x and the negative 6x, and that's going to give me x squared minus 5x, and then I'm going to subtract the 4 to the other side, so that's going to give me a minus 6. When I factor that, each one gets an x. They're going to have different signs, and we're looking for two factors of negative 6 that add up to negative 5 with different signs. So this is going to be a negative 6 and a positive 1. Then I'm going to break it apart and set each part equal to 0. So x equals negative 1, or x equals positive 6. But I need to first check my answers before I can state any final answers. So I'm going to check when x equals negative 1, and I'm going to check when x equals positive 6. For when x equals negative 1, it's 1 over negative 1 minus 6, so we're plugging into the original equation, plus negative 1 over negative 1 minus 2 equals 4 over negative 1 squared minus 8 times negative 1 plus 12. So this is going to give me 1 over negative 7 plus negative 1 over negative 3 equals 4 over 21. If you type it into your calculator, this gives you 4 over 21 equals 4 over 21, which is correct. So x equals negative 1 is a solution. And when we look at x equals 6, and we plug that in, right away, you plug it into the first fraction, and you get 6 minus 6. You don't even really have to show me the rest. 6 minus 6 is 0. 1 over 0 is undefined. Therefore, this is an extraneous answer. So x equals negative 1 is the only solution here. Now, when you're solving a rational inequality for a variable, we're going to solve first by cross-multiplying. And we always start in the top left-hand corner. So this is like saying 0 over 1. So that's going to be x squared minus 2x minus 15 times 1, which is just itself, is greater than or equal to x minus 2 times 0, which is just 0. Now we're going to factor this. We're looking for two factors of negative 15 that add up to a negative 2 and have different signs. That's going to be a negative 5 and a positive 3. I break it apart. X plus 3 is greater than or equal to 0, or x minus 5 is greater than or equal to 0. It tells me that x is greater than negative 3, or x is greater than or equal to positive 5. Both of them greater than or equal to. So that means I'm going to have a closed circle at negative 3, and I'm going to have a closed circle at positive 5. Now the other restriction that I need to take into account is the denominator. The restriction that this has is that x cannot equal positive 2, because then the denominator would be 0 and it would be undefined. So I'm going to put an open circle at 2 because it cannot be 2. Then I'm going to pick a point in between all of these points. So 1, 2, 3, 4 parts it's broken up into. So I'm going to test when x equals negative 4. I'm going to test when x equals 0. I'm going to test when x equals positive 4. And I'm going to test when x equals 6 in the original inequality to see if they work. When x equals negative 4, negative 4 squared is 16, minus 2 times negative 4, so that's plus 8, which gives me 24. 24 minus 15 is going to give me a 9. And then over negative 4 minus 2, so that's going to give me 9 over a negative 6. And they're saying that's greater than or equal to 0. Well, a negative number is not greater than or equal to 0, so that makes no sense. When I plug in 0, I get 0 squared, which is 0, minus 2 times 0, which is 0, minus 15, over 0 minus 2, which is a negative 2. We know that a negative divided by a negative is a positive, so this is greater than 0, so this point makes sense. So that means we're going to connect these two circles because the points in between them make sense. When we plug in positive 4, 4 squared is 16. 16 minus 8 is 8. 8 minus 15 is going to give me a negative 7. And then 4 minus 2 is 2. Again, a negative number is not greater than 0, so that makes no sense. And then finally, when x equals 6, 6 squared is 36. 36 minus 12 is going to give me a 24. 24 minus 15 gives me a 9. Over 6 minus 2, which is 4. 9 over 4 is greater than or equal to 0, so this also makes sense. So I'm going to draw an arrow going towards the numbers to the right because those numbers also make sense. Now, writing our answer in set builder notation, you use curly brackets. X, given that x is in between, it's including, so or equal to the negative 3, but it's just less than the 2, or, because there's a gap in between, x is greater than or equal to the 5. In interval notation, closed bracket on the negative 3, but because it includes it, up to 2, not inclusive, or including the 5, up to positive infinity, not including positive infinity.